So, meanwhile, I can introduce Daniel. Daniel got, as is working in security for a couple of years, I would say now. Yeah, he became famous with the Meltdown, hardware security breach, and for his PhD, he got the kind of PhD award of the Austrian Computer Society, the so-called Heinz Zemanek Award. He continued his work. He has he's a ERC from the European Research Council, a grant awardee in where he got the starting grant. And what is really interesting, especially for our lecture series, that he looks at security kind of certificates and yeah, very good. You have in them jumping left and right and up and down on the slide. This is very nice. And looking at security measures which nevertheless save energy. And this is really, and I think one of the hottest topics when we look at the numbers, and I guess we will hear more about that. Daniel, thank you for being here, and it's your floor.
All right, yeah, thank you for the kind introduction. I just realized I haven't started at the first time, so yeah, maybe we can start right there. So we will talk about security, and the question is always whether security is too expensive. But then the other question is, well, what if it's more expensive to not have it? And my area of security is this specific, very special area that is about side channels in a lot of cases. Side channels are obtaining metadata and deriving secrets from it. You might get other definitions from the books, but if you think about them a bit more, I would stick with this definition because this really includes a lot of side channels that are otherwise not included in other definitions. One example for give me just 1 second because I just realized that it's skipping some slides and I don't want that. Yes, now you can see all slides. Yes. So if we go through examples of side channels, then for instance, you could be thinking about profiling the utilization of the cache with performance counters. And the performance counters tell you how much cache utilization you have. Is that a side channel? No, because you are just using the performance counter to read this information, but you're not deriving anything from it. So it's basically just the information that you are supposed to obtain from this information channel. If you now take a step further and use those performance counters to infer a cryptographic key, as we did in several papers, then yes, that becomes a side channel. If you measure the memory access latency with flush and reload, also an attack, side channel attack, often called a side channel attack, the question is this already a side channel attack? And I would say, no, it's not a side channel attack yet, because you are just measuring the access time, and that's what you're doing, right? There's no inference of any secret. But if you measure it and then use it to infer keystroke timings or cryptographic key again, or other things like what the user typed, or where the memory is mapped off the kernel, then it becomes a side channel. So the question is always, what do you do with this information? If you just use it in the intended way, it's not a side channel. Yeah. One thing that we also learned over the years is that a lot of these side channels suffer from noise. You will find this all throughout the papers. Oh, there's a lot of noise there. There's a lot of noise there in these side channels. There's a lot of noise, and you have to rerun the attack many times. But over the years, we learned that there is no noise. Any noise is basically just data that you should, I don't see, Are you seeing this? I'm not sure you see the same slide here actually. Because okay, it was not updating for a second. Okay, yeah, there is no noise. It's just someone else's data that you haven't understood fully yet. And for that reason, these are always cases that you can look more into. One such example was we found around it was later known as transient execution. When I cook something, what I always do is I first put all the things on the table, and then I realize that something is missing. I have to go to the grocery store, and then I can go back to the cooking table, realize, oh no, there's something more missing. Then I go to the grocery store again. This happens to me something like 5 to 10 times, and then I have all the ingredients at home. And I invented a concept there that actually helps against this problem of having to go to the grocery store 5 to 10 times for any recipe that you want to run through. And this is what I call the food cache. This allows you to buy food or ingredients in advance and then store them at home so that you can later on use them. It's pretty ingenious. This concept, of course, I took some inspiration, and I took inspiration actually from processors. Processors have such caches, so that when you access data, the data is loaded from the grocery store, so from the DRAM in this case, from the slow memory into the processor, into the cache inside the processor. It's stored there, and whenever you access it again, it will be served from the cache. But of course, there's less space in the cache than in the main memory, same as you have less space in your fridge than in the grocery store, of course. So the first access, grocery store, DRAM, that one is slow. Second one is without the going to the store, that one is fast. That's a timing difference. And that's, if you speak to anyone from my team or anyone from the side channel community, then this is already something where they are like, oh, there's leakage there. This is definitely something. Yeah, so we can mount our first attack. And this attack works by looking at whether the access was fast or not, and by controlling what is in the cache and what is not in the cache. The thing is, shared memory, if you have shared memory, shared libraries, binaries, anything on your computer that can be opened by multiple users will be, in principle, shared. And so you have shared memory, it's shared in memory, so it's also shared in the cache. The same cache lines are used for both processes, the attacker process and the victim process. Now, the attacker can flush this memory location. This doesn't need any permissions, just read access to the shared library, shared object, binary, whatever it is. And then it's not in the cache anymore. And the attacker knows that. So the attacker now expects a slow timing unless the victim performs an access in the meantime. Then the attacker will observe a fast access time. So it's fast if the victim accesses the data slow, otherwise. And we're speaking here about a granularity of 64 bytes. So that means the attacker can monitor every step, everything that the victim does, like with a debugger, just on a granularity of 64 bytes. So that's a bit coarser than with a debugger, but it's fairly powerful. Actually, not very nice that it's so powerful. And this attack still works today. It's not mitigated. We don't really know how we should approach this one. So it's still possible. This is what the histogram looks like. So you have hits and misses. Very easy to separate. Even if you give this to a first semester bachelor student, they will be able to separate those two timing distributions and distinguish hits from misses. What can you do with that? For instance, if I let this run on the libgedit, which is part of the gedit editor, and print how many cache hits I get while typing in the editor. I'm trying to build a cause-effect relationship here. And then I just take any of those lines, which I believe has a cause-effect relationship, cache hits because of the keystrokes. And then I print a message every time that I see a keystroke. I get exact timings for every single keystroke. And this is already enough to train a neural network and then predict what words I enter. And this is, of course, problematic because then anyone without any privileges, you can see this, without any privileges can monitor what is going on in the cache, what is going on, what you're typing in other applications. And sometimes it's even worse. For instance, the libGDK part of the GDK framework for a long time used a binary search to determine what key code translates to what, for instance, UTF-8 character or Unicode character, whatever you're using on your system level. And in this binary search, the leaf nodes are only accessed if it's specifically that key. You can see this, for instance, there are addresses where you can single out the letter N or the letter V or the letter Q, and you can then say, well, I know exactly where those keys were pressed. I can tell which position in the password they have, and I know for sure that it's this letter. But with that, it's not enough. We can do more. We can do even worse things. And we will use the same principle, flushing and reloading memory, but this time we will attack something different. In this example here, we access a kernel address. You can see this with a lot of Fs, and then this 8, 1, A, 0, and so on. This is a kernel address. There's something from the kernel at this location. So if we would run this code line, we would get a segmentation fault. So this would crash our program. But that is not a problem. We can install a signal handler, and the signal handler can catch the seg fault, so our application then won't crash. The next thing that we do is, so we load this location into a character variable, 1 byte. Then we access an array with this character variable. And yeah, we don't care what we do there, we just access it. Now, if this code line is executed, if both code lines are executed, and the data is passed from the first code line to the second code line, then we would be able to read kernel memory with that, because the array index that is now accessed depends on what the secret was that we just read from the kernel. So this is not a side channel attack. We're not using any metadata here. We're directly getting data from the kernel, and then we are deliberately accessing a memory location, and then we're deliberately testing whether this was the memory location corresponding to the index that we read. So this is not a side channel. It's more powerful than a side channel because we immediately get the data. So we just check whether any part of the array was cached, and then we see, well, yeah, this works. This is the Meltdown attack. This worked on a bunch of systems. This is, for instance, a Samsung phone. Meltdown worked on a lot of Intel processors, most Intel processors, also a bunch of ARM processors, including iPhones, including some Samsung phones, including some Qualcomm processors. But mainly in the media, it was just Intel in the media. But of course, then, yeah, that's what's in the media. This video shows you that if you know a physical address, you can also just go and find the kernel identity mapping, so the direct physical map in the kernel, and then you can just, while the user types, read from this address, and you will get every keystroke. I'm not sure why the video is actually lagging at this point. Now it's not lagging anymore. Yeah. So while you're typing, you can just read the string while the user is typing. So much, much more powerful than a side channel attack, way more powerful. And yeah, next one, I'll skip this one. I don't need to show all the exploits. So we came up with a solution. And this solution to the Meltdown attack, we call it Kaiser, kernel address isolation to a side channel efficiently removed. And we thought, like, it's a pun because we have the Kaiser penguin, the emperor penguin, and it's a patch for Linux. So it makes sense to make the Linux penguin stronger, more powerful, the emperor, basically. Also, it has some connection to Austria in a way, which we also liked. And this patch actually is fairly simple. So with traditional operating systems, you have a shared address space between user space and kernel space. So you have the same address space, and you only context switch between those by changing what addresses you're executing at, and by flipping one bit somewhere in the processor which says whether you are currently in kernel mode or in user mode. Now, this is a problem because that means all the addresses, even if I'm not in kernel mode, the addresses still exist. And that was the problem of the Meltdown attack. We still were able to access this memory location, and the processor was, yeah, I would say optimistic enough to actually hand us this data. No one thought that someone could escape from this seg fault and then actually continue with this data. No one has spent a thought on that. but we can, and now we have to change that. So we can't leave the kernel memory there. The kernel memory shouldn't be there. So what we change is we unmap the kernel while we are in user space, and then we have a context switch when we enter the kernel, an address space switch, so that we are in a dedicated kernel address space. And so almost nothing is mapped anymore in the user address space. And then if almost nothing is mapped, then there's almost nothing that you can leak. This was one of the two transient execution attacks. It's not a side channel, but it's very related because internally it uses flush and reload, but it's not a side channel in its entirety, so the entire attack. There's a second transient execution attack, and then a lot of attacks followed on that. A lot of variations, a lot of variants of Meltdown, and the other one that is called Spectre. So for Spectre, I will go back to one example. When we discovered these attacks, we had a pizza place near to our university, and we always went there for lunch, and it was always the same. People were ordering different pizza, but there were at least something like 4 Diablo pizza. And we typically called there, reserved the table, and said, we will be there for lunch. We like a table for 6, please. And they were like, yeah, we know you guys from Graz. So we can already start making the pizza because we know they will always get at least 3 Diablo, at least, right? No one changes their opinion. They always get the same things. And this is what we call speculative cooking. And you could have figured this out by just calling the restaurant and saying, table for 6, please. Of course, they would not recognize on the phone that it's not actually someone from Graz. So you would be able to pretend, yeah, we're from Graz, so please give us the table. So if you do that, then they would start making the pizza, and the pizza would already be there, and you can already smell it. And a very good, with someone with a very good nose could smell that it's the Diavolo pizza, although the pizza cook does not hand out the pizza. And this is pretty much what happens here with Spectre. So let's take a look at the code. We have this index here. Index 0 is, so we have an API where you can choose an index for a character that you want to read. And of course, we have in this API a bounds check, which makes sure that we can't read any of the secrets, in this case, the secret key. So anything below 4 is allowed. Anything from 4 onwards is not allowed because it would actually leak a secret. So this is not going to be accessed. Or so we think, right? Bounds check, best practice. They always told us put bounds checks everywhere. But the problem that we have there is that the processor will actually speculate all the time. It might speculate in the wrong direction and then execute the right direction. And by doing that, the processor will learn what is the right code path. So, and after a while, the processor will actually always speculate in the same direction. And as soon as you reach the secret key, the processor will still speculate and perform the memory access, and by that, leak the secret information. So this is pretty problematic because with this, again, you can read data that you should not be able to read. Yeah, we have this illustration for Spectre where basically a bunch of operation follows. 3 operations are shown here. The operation before the prediction, then the prediction, and then the operation afterwards. And we have 2 types of predictions, the data flow or the control flow, both exist. And there is some window in which we can perform follow-up operations. As soon as the prediction, as the instruction responsible for the prediction retires, as soon as that's the case, everything will be stopped and everything will be thrown away and reverted. But the problem is that changes in the microarchitecture persist. For instance, changes to the cache state, they remain. For Meltdown, it looks a bit different. There we have an exception. The data is not thrown away. It's passed on to follow-up operations, and that's a problem. So no prediction there. We just pass on the data, although we should not. There are lots of different variants. I won't go into the details, but this gets me to the important point that I wanted to get to. Sorry for taking so long to get to the main point here, and that is mitigating these attacks is kind of important, because if every website can just read your kernel memory, not just the kernel memory, any memory on the system. When I found Meltdown on my system, so we co-discovered, several people found this at the same time. When I ran the first experiment on my system, the first thing that I leaked was a long URL. And it took me a few minutes until I realized where this URL was coming from, because this was an advertisement company. And I was like, I've never visited this website from an advertisement company I haven't even heard of before. And then it turned out that this URL was on my ad blocker list in Firefox. And that was immediately the point where I realized, oh shit, we can leak anything with that, anything from any program running on the system. Pretty dangerous. That means I can't have secrets on my system anymore. And we need to do something against that. Kaiser, one of the mitigations, right? But for Spectre, we need another bunch of mitigations. And all of them come with a performance loss. You can see here 22% performance loss. There's a bunch of Intel measures in the middle, IPRS, STIBP, and IBPP. There we have 20 to 30%, 30 to 50%. This is making our systems much slower. And this also means we will need to buy more computers to do the same computations as before, for instance, in the cloud, more computers, which also means more emissions, more electricity consumed, more computers that need to be manufactured. So this is all pretty bad. There are more problems. I will just tell you about one more that I also find particularly interesting, and that is not a sanction attack anymore, also not a transient execution attack. This is actually the hacker used a DRAM row hammer. Sure you actually hear anything. So basically, it's from a show called Designated Survivor, and this guy just got shot after he discovered that a satellite in space was attacked and hacked with a rowhammer attack. So yeah, so rowhammer made it into popular media. This is a screenshot from my own first rowhammer paper. This was from 2015. And here I is there yeah, if there's a question, you can always ask the question because someone raised their hand. So if you want to, we can handle questions in between. Otherwise, just at the end, whatever you prefer. All right. So so this was from 2015, and what we did there was we ran this rowhammer attack from a browser and were actually able to induce bit flips in memory. And we also showed that in having those bit flips, the bit flips that we saw, if you then trigger them again manually, like because the entire attack takes a long time, then you can actually get root privileges on this system. So basically what you can get is root privileges, kernel privileges on a system just by running some JavaScript, which is pretty bad because that means any website could actually do this and read all the memory of your computer, install backdoors, change memory contents, do whatever they like. For ransomware, this would be awesome. They could infect any system on the planet. Very nice. So how does rowhammer work? Your memory is actually, I mean, you want to store bits, right? Bits are 0, 1, and they have to be stored somewhere. And it's actually an array with a lot of capacitors. Every capacitor stores 1 bit. So you have millions of capacitors in there. And these capacitors lose charge over time, which means that you need to refresh them from time to time. To read the values from the capacitors, you actually have wires running through this array, the so-called bit lines, and then the capacitors of one row are opened, and the charge flows onto the bit line and down into the row buffer at the bottom. So basically, by activating a DRAM row, by reading it, you copy the value into the row buffer. Now, there's one effect that people for a long time were not aware of, and especially so when they were aware of, for at least a decade, they did not realize that this could have security implications. And this effect is that cells leak faster upon proximate accesses, upon accesses in proximity. And this is the rowhammer effect. So if you access two rows, for instance, very often, there is a high chance that in between those two rows, the middle row that you can't access, that you have no permission to access, that this one has bit flips. So you change memory contents without having any permission for that. And it's pretty bad. This is also, this is the first variant that was described was this one, where you just hammer random locations. You see bit flips next to one of them at some point. Then the more advanced, the double-sided hammering, the one that I've shown you before, where you hammer two rows that are right next to each other. But there are more. There are more. Because we also discovered that just hammering a single row, also depending on the system, can induce bit flips next to it. More recently, so this was in 2020, then together with Google, we discovered that actually hammering like this also can induce bit flips on some systems if they use target row refresh, a mitigation that was supposed to mitigate row hammer attacks, but then again, it didn't. And this is a big problem because if you don't understand how an attack really works, what the effects are and what the reasons behind it are, then you build mitigations that don't really work. And yeah, this is pretty bad. This is just one video of a row hammer attack. Yeah, you will see a bunch of bit flips. That's it. I recorded that at some point. And then what do you want to do with those bit flips? For instance, if you flip bits in opcode, for instance, in a jump equal instruction, let's see what happens if you flip one bit. You can change it into different jump instructions, including jump not equal. Great. So if you have the pseudo binary and want to enter a password, and you type in the correct password, now it will say wrong password, but any wrong password will actually lead to pseudo privileges. Very nice. There's more. There is more. I will go for one more attack, and then we will talk about what we can do to improve the situation. So the last attack that I want to talk about is Plunder Vault. And this is actually, this is a piece of code that you can briefly take a look at. It's an endless loop. We have a multiplier here, we have a variable correct and a variable var. And correct is just initialized to a value. Var is also initialized to the same value. And while they are the same, it should just continue. And you can see in the loop, we set var to the same value again. So this loop should never exit. So let's see what happens when we run this. So we run this. We run this a bit differently. So in this case, also with sudo, because our attack target in this case is a trusted execution environment. That's just the question of the threat model. Let me just skip a bit ahead. Let's see whether that's possible. Yes. Yeah, so we changed the voltage of the processor via some MSR, and that is possible. That is also perfectly allowed. And then if you change the voltage, so we are now reducing the voltage by, let's say, 250 millivolts, then we see actually, but at 259 millivolts, we see that there was a miscalculation. Oh no, so this is actually a security problem. And you can see that this is very consistently, if we go below some threshold, that we see faults. We start seeing faults. And as you have seen now, this went down from about 750 millivolts to something like 500 millivolts. So we are undervolting quite a bit there to get faults. Okay, so we are undervolting quite a bit there to have faults. Maybe we should plot that. So if we take a look at this plot, then we can see that actually there is a big margin, pretty big margin between the base voltage that is currently configured when you buy the processor and how low you have to go to get a fault. Let me just, okay, I will skip this next attack. We don't need to know about that one. So we came up with a nice name, Plunder Vault, sure. And that was basically And as a consequence, Intel actually addressed this by removing this undervolting interface. But this is maybe not so nice. We will take a look at that in a second. Before that, I want to get back to the overheads. Now that we've seen all these attacks, if we now want to mitigate them, for instance, for Chrome, the mitigation against several of these side channel attacks, including Spectre, is site isolation. And on Chrome, we get plus 8.2% of performance overhead. So that means you will need this much more compute resources. Things will be that much slower. You will use your computer for a longer time. Your computer will use more energy while you are using this because of this Spectre vulnerability. For Meltdown, we had the Kaiser patch with roughly 5% of overhead. And all of this is pretty bad considering that we already have growing energy demands with our global ICT. This is a study from 2017. So this was before the Bitcoin bubble. And this was also before the AI bubble. And they projected back then, before those two bubbles that are still ongoing, that 21% of global electricity demand will be consumed by our ICT. A lot of this in data centers, a lot of this in networks, consumer devices, and also a bit of it in the production of our devices. Now, 5%, 8.2%, yeah, it doesn't sound too bad, right? It's just my laptop, right? Who cares, right? And in 2018, when we published the Meltdown and Spectre attacks and also the mitigation against it, I got an email that asked me, so you're making everything slower. Don't you feel guilty about that? Because it's not good if you make everything slower. Everything consumes more energy now. That's not good. So I ran the numbers, just ballpark numbers, just a napkin calculation, basically. So what we want to understand is, what's the overhead of Meltdown? What was the overhead of Meltdown? In 2018, electrical energy was 7%, so 7% of that went into our global ICT. 7%. And if we translate that to greenhouse gas emissions, that's less than 2% of greenhouse gas emissions, global electricity. So the electricity demand for our global ICT. The Meltdown patch in 2018, if you just run 5% of that, roughly 5%, I ran this with accurate numbers, I got to 0.09%. If we just apply the Meltdown patch to all of the ICT emissions, which is a bit of an overestimation probably, but it gives you a ballpark number. It will not be 10 times as much. It will also not be a tenth of that. It will be in this order of magnitude. 0.09% increase of greenhouse gas emissions from a single patch, that's substantial. And now if we do the same in 2030, when 25% of global electricity will be consumed by our global ICT, which might need a patch like the Meltdown patch, 5%, suddenly becomes 0.4%. And that's a lot, considering that some estimates say that global air traffic is something like 1%, some more pessimistic ones say 2%. But 0.4%, what do you want to rather have? Air travel, or this one patch that makes all your systems slower? People will not want that. So people don't want to make systems slower, consume more energy. It's all bad. It's not sustainable. No one wants this. So at this point, we have to face the facts that there are alternatives to security. If we just take the CO2 price fully into account, it might be cheaper to just turn off all security and just run insurance companies that compensate people for their losses. You could say, for instance, oh, you got ransomware again, or you already had it last month. Here, take 500 euros for compensation of your damage. And if we all pay our premiums into the insurance company, then maybe they make a profit out of that. maybe that's the future. The problem there is we don't really know how expensive security is because no one is looking at that. I actually went through 484 papers, all of the top security papers. We have A-star security conferences. And I looked at all the papers in those conferences from 1 year, 484 papers, and only 6 out of them mention energy efficiency or anything, any word that I could map to that. 2 provide energy cost. 2 out of 484. So actually, we don't know how expensive it is. So what we did, and this is a recent study, I'm presenting it this year for the first time here, we actually went and tested 108 Linux kernel CVE fixes. So these are vulnerabilities in Linux. And we looked at how much energy overhead do they have. We measured the energy overhead in standard benchmarks before the fix and after the fix. And we also measured the runtime overhead. And what you can see is that these two are in general correlated. So if you have more computation time, then you will also have more energy overhead, and it will be largely proportional. You can see how well this line fits in there. But there are some outliers. Around zero, there are some cases where the energy overhead goes up by 2%, although the runtime stays the same. And these cases are interesting because this is something that the security community is not aware of. We are not measuring energy ever. We are only measuring runtime overhead in 99% of the papers. More than that, actually, more than 99%. If we take a look at hardware mitigations, so if there's anything to be solved in software to address hardware flaws, hardware security flaws, we can also see a similar picture. Also here, largely correlated, but there will be some cases which are not correlated, where, for instance, you have a runtime overhead but no energy overhead, or where the runtime overhead is basically zero. We don't see a deviation from the runtime, but we see a deviation on the energy overhead. Actually, both in a positive direction, and there's also a case where with the security patch, the system got much more efficient, 5% more efficient. Same runtime, security patch, 5% more efficient. That is weird. So these are interesting cases to look at. And we did that in a paper. We published this in Asia CCS this year. So if you want to take a look at that, you can look at the single cases. And we did some case studies and looked at why these get faster. For instance, the one at the very bottom that you see at minus something like 6% or something, and runtime overhead of almost zero. That's actually a patch against speculative execution attacks, which stops speculative execution in cases where it won't be successful anyways. And the rare cases where it's successful, yeah, in those cases you have a performance overhead. But in all the other cases, you just save energy because you stop the processor from doing completely nonsensical stuff. So, yeah, the security community. I talked with a lot of people from the security community, and I was saying, well, we should do something about that. We should mitigate this issue, and we should actually be on the forefront of this. We should actually be the first to mitigate this. And the response that we get is typically people saying, why us? Actually, the machine learning people, they consume way more energy. What about Bitcoin? Bitcoin consumes much more energy. So why should we be among the first to care about that? Well, the problem is that we don't have a choice as the security community. As I already showed you before, there's costs. And then if people have the choice between security and something else, they will choose something else. For instance, security versus functionality. You see that people don't use good passwords, that they are bypassing screen locks, that they are bypassing security mechanisms all the time. Because security is not nice. Functionality is nice. People want functionality. They only take security because they have to, because otherwise, yeah, my system would get ransomware again, yet again, second time this month. Yeah. And of course, the question is, if I ask the question, what will people choose when security becomes too expensive? This is crazy. I've given talks to people in the security community and asked them, okay, what do you expect? What will happen when things get more severe, when resources become more scarce, and we actually can't afford or affording security is gets more tricky. Who thinks security will still be the top priority? And if you talk to security researchers, a lot of hands go up. And if you talk to people outside of the security community, I had the opportunity to talk also to audiences that were less security affine, then you actually realize that they totally don't care about security. They absolutely don't care. And they will actually not consider this any problem at all. And they would just say, well, nothing happens all the time anyway. I'm not using a good password and no one hacked me yet, so it can't be that bad. The problem that we have now is that, so in the past, we had Moore's law that always saved the day. Moore's law allowing us to compute more for less energy has been working for a long time. Unfortunately, Moore's law is ending. We all know that it's slowing down. It's only a matter of time until it's so slow that we're not making any progress anymore. And you will actually see this, you might see this actually with your own computers. If you think about a computer that is 10 years old from 2015, you might still be using a computer from 2015 and it's still working fine. But think about a computer from 2005. This jump from 2005 to 2015, this was a massive jump that you could really see. But we don't see this jump in efficiency and in performance anymore. And so people can stick longer with their computers. So Moore's law is dying. We can really see that. So what we as the security community now need to figure out is how can we make ourselves important in a way so that people cannot remove us from the computer equation, right? So if you build a computer, you will need functionality, you will need reliability, otherwise the user complains. So the reliability community already managed to get there. So if you get reliability out of the system, people would complain. But if you remove security, people won't complain. So we need to make sure that security takes this position. And actually, I did this. I wrote project proposals where I said, we need to replace all reliability mechanisms with security mechanisms. And I believe that is the case. We should get rid of all reliability mechanisms and replace them by stronger security mechanisms because we can achieve more, we can make our systems more efficient. And people from the reliability community totally don't like that. I got project proposals rejected where it was clear that the reviewer felt personally offended by me saying that they are doing it wrong. So this is something that I can't recommend. Don't offend anyone, but still, if you have an idea, so I got I had this crazy idea that I could replace. We get to that anyways. So I had this project proposal that I submitted to Intel several years ago, there I said, well, we can do something different in the memory, and then. This will be better. This will lead to better properties, more reliability, more security, and actually also more performance and more efficiency. And then one of the reviews said, well, you don't believe that you can really do this better than how Intel is doing this since 40 years, right? We are the expert on the topic. So it almost literally said that. And that was really interesting to see, because if someone tells you, you can't do this better than we do this since 40 years, you can imagine how many other brilliant people before you have been shut up with the same argument. And probably there's something to find there. If someone says, don't look at that, no, you can't do this better than we did this 40 years ago, and we stuck to this principle from 40 years ago, and we didn't look at any new developments. Don't look at that, it's already perfect. You can be sure that you will find something there. Yeah, so this is my question that I want to ask, and the question that I also pursue in my ESC grant. that was mentioned in the very beginning. Can we make things more efficient by adding security? So we want to do more security, and by that make things more efficient. And this is actually counterintuitive because doing more computations should cost something. But we already had this little indicator before where we saved 5% by applying a patch against speculative execution attacks. This is interesting. So there might be cases where adding security actually makes things more efficient. So let's take a look at the first example. This is also some new results from this year. We call it SMT cache. The idea here is to introduce multiple caches instead of a single level 1 cache into the processor. And the processor will switch between those, and no two security domains, like processes, will run on the same slice at the same time. However, overall, the cache capacity gets much larger, and with this, you get a performance gain. So this is very nice. You get a performance gain. And at the same time, so the question is, can we save energy? And yes, if you would get the same cache capacity without these security domains, you would actually be an order of magnitude larger on the energy consumption of this. So actually, adding a security domain there allows you to save a lot of energy. There is another example that we already briefly saw before, this undervolting thing. Undervolting, I always make this poll in the classroom, but now I can't see you, of course. But in the classroom, I often ask, okay, so undervolting. I did this already in the past, and you can just undervolt the system. You can reduce the voltage. And the question is, does the performance of the system increase by undervolting, or does it decrease? And then typically a lot of people say, oh yeah, I raise the hand for decrease because you reduce the voltage, so the system can't do as much, right? The opposite is the case. It's actually getting a lot faster. You can actually, on modern computers, often get more performance by undervolting than by overclocking, because the CPU is not limited anymore by the clock frequency mainly, but by the power budget. It cannot run in turbo boost mode all the time. It cannot run at the highest clock frequency all the time. But if you reduce the voltage, it can do so more often. And so you get a lot of performance for free. And I've actually been doing that on all of my systems since 2007, around 2007. And I've undervolted those. And I actually had a lot of extra battery runtime. So my current laptop, that's from 2018. And this one, when I got this brand new, it had stock under Linux, 12 hours of battery runtime. With undervolting, 23 hours. 23 hours of battery runtime on Linux, on a laptop. That's not bad. And it's not a big laptop. It's a very nice small laptop. 23 hours of battery runtime for free. At the same time, it was not running as hot and it was running faster. So it's faster, less hot, and my battery lasts longer. That's a no-brainer. Why wouldn't everyone do that, right? I ran my systems totally fine for 10 years like that. And like, there was something. Yes, there was this thing with Plunderbolt, with the while loop, and then where we have these errors, right? So the question is, can we exploit this maybe more efficiently? Can we maybe say, we don't want to have the same security margin all the time, but just depending on which instructions we execute. And actually we can do that. So we actually did that. So we looked at this case, and actually the voltage, there is some part in there which is we call instruction variance, up to 150 millivolts in there. We see faults for some instructions at the upper border of this, where for other instructions, we don't even see faults at the lower, or we start to see faults at the lower boundary of that. So about 150 millivolts that we could save by splitting instructions into two groups and running the system on two different curves. One efficient voltage curve, and the other a less efficient, the conservative, so the current voltage curve. And we can switch between those curves. For instance, we could ramp up the voltage. We could decrease the frequency. This is actually faster. Decreasing the frequency is much faster than ramping up the voltage. But it has the same effect. We are moving from one curve to the other. And this is actually what our mitigation then does. It reduces the frequency first, and then as a second step, if we want to run faster, it can increase the voltage again. We implemented this in a simulator, and we measured this actually on real hardware, how much we can save on real hardware. And there we see that we can, on multiple processors, we saw energy efficiency gains of plus 20% for free. The system was just running as fine as before, 20% efficiency gain. And we believe that we can even do a lot more if this is implemented for real in a real processor, because then we can push those limits much, much further and maybe even get to something like plus 40% on energy efficiency. Yeah, so that's definitely something. Adding security, so we add the security mechanism, which splits those two instructions into save and not save. And by doing that, by doing more, we suddenly save 20% on efficiency. What about other problems? What about, so we mentioned side channel mitigations. There are some cases where it gets faster, undervolting, some cases where it gets faster. The caches, where we can get more performance without an equivalent increase in power consumption. Rowhammer, we mentioned that one before. What about Rowhammer? Why is this not solved yet? Why are people still talking about Rowhammer? There was just last month a new variant, or I think in this month, a new variant coming out which again showed that a bunch of mitigations don't work. They released a lot of mitigations that were focused on, you need to hammer these two rows. But then we discovered, only a single row, and all of the mitigations stopped working. Then people realized, it's not the two neighboring rows, but two further away. All the mitigations stopped working again. Now they realize, you can also hammer different offsets within a row and get bit flips from that. So how incapable are we even at mitigating such a simple problem like Rowhammer? And the problem is that we very often misunderstand how the attacks work, and this creates bad incentives for mitigation. Because we are like, let's just mitigate this. Like Rowhammer creates a single bit flip, so let's just add one more bit for reliability, and then we can check this, right? A parity bit or something. The problem is that this actually doesn't change anything. I will get to that in a second. Other arguments were like, just refresh a bit more often and then you will not see the bit flips. Or just add ECC memory everywhere. The question is, what incentive does it create? Now, from the perspective of the attacker only wants to have a single bit flip. The attacker does not care whether this is a system with ECC, with any other mitigation. The attacker totally doesn't care. They just want one more bit flip. One bit flip more than the system can handle. And that's the problem. With ECC, we are just moving the target by a bit away from the current status quo. With the mitigations like TRR or anything in that direction, we're just moving the one bit flip a bit further away. And this is a problem. This is a really big problem, and this creates the incentive on the one side for manufacturers to again optimize everything out of their system. And we saw this happening for mobile phones. Mobile phones now all have ECC memory, and still we see bit flips on those because we just optimize them to the absolute limit, and we don't care that we see bit flips. And then, no, it's a new Rowhammer attack. So this actually happened. Apple introduced ECC in 2018. The others followed very quickly. And then they at the same time said, let's reduce the refresh rate because now we have ECC. We don't need this anymore. Let's optimize for battery runtime. And then again, we have bit flips. So this is an optimization problem. And you never know how far is still safe. Safe and reliable also changes over time as you discover new attacks. Because the problem is, not like in the reliability community where they are like, we can estimate how much cosmic radiation there is. We can't do that. The adversary is intelligent and they can improve attacks over time and improve attacks based on what we as defenders do. So this is really, really bad. And we need to think about mitigating these attacks in a way that cannot be bypassed. When I started my PhD, people told me that security is basically reliability plus something on top of it. And I believe this is a lie. Reliability is just messed up security where you don't want to define who is the adversary. So we need to get rid of reliability. You always need to define what can go wrong, what can the adversary do in the worst case. If you don't define that, you're not doing proper science. So let's get rid of this, like, oh, let's assume normal background radiation. No, let's assume what's the worst that can happen and how does the system handle this. And then it's fine to say, well, we don't handle this and this and this. But please define those cases and don't say, oh, natural background stuff. No, there's no natural, today not anymore. Then they say stuff like, well, we assume normal conditions without any adversary on the system. What does that mean without any adversary on the system? We are all running JavaScript code from dubious websites that none of us has looked at. I don't know what this JavaScript code is doing. There's always an adversary on our systems. Even right now, I haven't looked at the Zoom code and you probably didn't as well. I don't know whether this is attacking all of our systems right now. So let's assume there's always an adversary on our system already. And the only thing that keeps this adversary from stealing everything is that we have some isolation mechanisms in there. Reliability folks ignore this. They have no idea of the real world. So let's please replace reliability with security. And I hope I didn't offend too many people here, but usually I offend a few people with statements like this. Also, take it with yeah, you can have a different opinion. Of course, I'm exaggerating a bit to make a point, right? So don't take it like, I don't want to make this sound too extreme, but in a way, yes, because I want to convince you of my point. Still, people say, that's against the rules, you can't get rid of reliability. So I want to use security for efficiency. I already showed cases for that. And I want to solve this now for Rohammer as well. And my idea here was to degrade the performance of bit flips without, so the performance of the system when you have bit flips. So only the performance is reduced, but you have no impact on the security. And we do this by replacing the error correcting code with a cryptographic MAC. Now, those of you familiar with, or at least somewhat familiar with cryptography, know that you cannot just break a cryptographic MAC. A cryptographic MAC cannot just be broken. If you would break it, you could publish that because of the way how it's constructed. So if a cryptographic MAC mismatches, then you would have a successful attack. You could publish that because the cryptographic MAC is broken. So this won't happen. So this basically in practice means that you can detect any number of bit flips because the cryptographic MAC won't match. Now, the only part that was missing, the only puzzle piece missing was how do we do the correction? And we tried to come up with the most stupid solution that we could come up with and published that. And it was successful. We successfully published that. And now processor vendors are introducing this into their processors actually. Correction by brute force search. So the idea is super, super stupid. We take the cryptographic MAC, we try to flip a bit, and we see whether the MAC now matches. It's super unlikely that we get an incorrect match because of the properties of the cryptographic MAC. How long does this take? Actually, super fast. So with single bit error, that's the only case that only the first line is the one that current error correcting codes can do. We are in the same order of magnitude on the correction duration. For everything else, we still can correct where ECC can't correct, and up to something like 6 bit flips within a 64-byte word, in a 64-byte data word, we are still in the range of seconds, so we can correct very, very fast. So this is pretty good. And the security guarantees are incredible because they basically just break down to the security of the cryptographic MAC. And that is basically you won't get silent data corruption in a bunch of billion years. The chance of getting a second pre-image after hammering for 1 year straight, non-stop, without a break, is super, super small. Even if you have an 8-bit error, the probability that you erroneously correct it to something else that mismatches is 0.01 something %. And 8-bit errors, you don't see those with Rowhammer. It's super unlikely that you see those with Rowhammer. So there's definitely something that we can gain here. And if we introduce this countermeasure, and that's why the vendors are interested in this, we can actually do the same as they did in the past, optimize the system further. But now this changes a bit how this game works, because now if we tweak the system too far, if we exaggerate it with the optimizations, with the overclocking, with the reducing refresh rates, then nothing bad happens. The only thing that happens is we need longer for correction. We just take a bit longer for the correction. So we lose the performance again that we gained by optimizing the system. So now we actually have a trade-off point that engineers can optimize for without losing security. And at the same time, if you would remove the security mechanism, you would actually reduce the system performance again. And with this, we get system security into the equation again, and we can't get rid of it without making systems slower. So with this, I would like to thank you for your attention, and sorry for going a bit over time and being a bit late. But I hope you enjoyed the talk, and I would be looking forward to a lot of questions and discussion, and maybe you can challenge some of my bold statements that I tried to make. Thank you.
Daniel, thank you very much. Yeah, genau, the new Zoom has this
I hope everything worked.
applause. The clapping hands going up. Very good. So we'll see if people jump in. Perhaps just as a kind of a,
if you have any
what
questions,
are the as an icebreaker question?
And you can ask a question, but
what are the cons of undervolting?
maybe my audio is maybe I don't hear anything anymore.
I can hear you. I can hear you. Can you hear me? No. So we have lost our speaker. Perhaps I should write it in the chat. I will write it.
Maybe you were already. So I need to stop maybe this one. I can now I can see you again at least. I can also see that you're talking, but
yeah. We can hear you. Yes, we can hear you.
Let me just rejoin, I guess, because maybe Zoom is confused about the audio.
Let's see if our speaker is coming again. I'm pretty sure.
Hello?
We can hear you, Daniel. Okay.
I don't hear anything. It's a bit weird.
We can.
I don't know why I can't hear anyone. I hope you were able to. Okay, you are able to hear me. It's a weird situation.
Perhaps there is a security breach.
So if you send me the questions, I definitely don't hear anything, not even locally. If you, maybe now.
I can hear you.
Yes, I can hear you again.
Very good.
I don't know.
So security holes.
No, I don't know what happened. Probably the audio.
I just said, what are the cons of undervolting?
The cons of undervolting, security problems. If you solve the security problems, it's for free. And I would actually, so I do that. I still have my laptop.
Yeah.
Risks, but the gains, I mean, if you get like, what was it, like 11 hours of
Yeah, it's amazing. Yeah. Okay.
I do that. Like I can live with the security risk there. And I'm saying that as a security researcher, I shouldn't, right? I shouldn't be advocating for less security, but 11 hours of battery runtime, having that versus not having that that's a no-brainer.
Yeah, and especially if you scale it up, also not only one person, but millions of people.
Undervolting the cloud that much, Amazon could gain, billions from that. Yeah. Or millions at least. But probably.
You were mentioning this, when just students out there ask questions, and if you don't ask, I continue with mine. You were mentioning this problem, having the password on somewhere written on your laptop. How to really reach usable security out there?
Oh, usable security, you mean where users don't misconfigure things? Oh, that's I don't know. That's a tough one. That's probably maybe the hardest question I ever got. There's a research area that is really skyrocketing at this point on usable security. One conference that is growing very, very fast, they are doubling every year, is called SOUPS, and this one is a symposium for usable security and privacy mechanisms. And they are skyrocketing because there are a lot of challenges that are not trivial to solve. Because at the same time, you don't want to. So the problem is always to make it usable. You have to make the interface simple. But at the same time, for security, if you make things simple, then it can happen that you implicitly misconfigure already, or that the specific default configuration is not suitable for you. So making security usable is very, very, very tricky. And it's also not looking to become easier over time, because security is getting more complex over time as well, as our systems are getting more complex.
There's a question in the chat.
Yeah, I can read that. Are Inspector and Meltdown fundamentally hardware problems? Yes, they are fundamentally hardware problems, yes. Shouldn't a correctly functioning MMU reject reads from invalid addresses completely? Yes, but the hardware does not always know whether an address is invalid or not. Typically, so you have these page tables in your operating system that the hardware uses. And typically, while translating those addresses, only at the last translation level, you know whether the translation was valid or not. However, while reading this entry, you might already want to read the data in parallel, especially if it's in a cache. You might already want to read the data in parallel. Sometimes you don't have to walk through all these tables, but you can use the TLB, the translation look-aside buffer, a small cache inside the processor. And yes, then you get the address where to look it up in the cache. So actually you have exactly at the same time, the address where to look it up in the cache and the tag to check whether this is the correct address. You get the data and the result, whether it was the correct address at the same time onto these wires. And so the challenge is actually to make sure that these wires don't run through into the register where they are that they are directed towards, if this other bit, if the security bit is not okay. So yes, I would agree for Meltdown, a correctly functioning processor shouldn't do that, because it should somehow, for instance, zero out the values. Zeroing out the values is actually not enough. We already exploited that. If it only returns zeros, we can still mount attacks on that. So it's a bit more complicated. For Spectre, I disagree. For Spectre, same as branch prediction, you're saying the results from false branch should be completely discarded with no side effects. That's impossible. You cannot completely discard this with no side effects. You can also observe the side effects in parallel, so you have no chance of mitigating those side effects. And then the only other option would be, well, to only do branch prediction if you know already that the prediction will be correct, but then it's not prediction anymore. So effectively, you would disable prediction. And we need branch prediction. So for Spectre, we are in a dilemma. We want and we need the performance gains and the efficiency gains that we get from it. But if we have that, then we also have the leakage. There's no way around that. It's a fundamental dilemma, and I have not seen good solutions for this problem yet. That is why all of your systems are still affected by Spectre attacks. Every system out there, any reasonable large processor will be affected by Spectre. And I don't see any near-term future where this changes. We don't know how to solve the dilemma. We want the performance. We don't know how to make it secure. And that's why things like site isolation are then introduced as a second level of defense. Maybe this is maybe a very important point to make here. As computer scientists, we are very familiar with the concept of divide and conquer. And I would argue that this is the only mechanism that we know how to make things secure. Try to reduce or minimize the compartment that the attacker compromises. Try to contain the attack. If the attacker compromises one of your processes, make sure that this process cannot compromise other processes. That's what the operating system does. And I would argue like this goes even further. This also, and this might translate to your university networks as well. Try to make sure that if one system catches ransomware, that it's only this system and not all the systems. And I think there are a lot of developments here that we need to take care of that are dangerous in a way, where we centralize everything with software that is connected to that connects every single system somewhere. And the problem that we have here is that it's not about can I secure my system, and will this solution that the central administration installs prevent me from getting ransomware? The question is, for all of the systems at the university, including those central systems that have all the permissions that you need, how likely is it that those never get ransomware? And the probability for that is larger. The probability is lower than 100%. So all of these systems eventually will get ransomware, right? The probability is greater than 0 that they will get ransomware. And now if you have a system which can actually deploy something on all other systems, oh, that's for attackers that are like, my attacker heart is like beating up, and like, yes, that's the system I want to attack. So if you want to do something good for the attackers, make sure that you have some software that has administrator privileges on every system, like these endpoint detection and response softwares. They are awesome for attackers, because if I compromise that one thing, that one central point, I got the entire university. And then I can get a lot of money out of that, more than from your single small laptop, right? Your small single laptop, like, how much will you pay for it? But the entire university, I will make millions. I'll be a rich man. Because the entire university also doesn't, not everyone has the backups, right? So I will be very, very rich. So as an attacker, you want as little compartmentalization as possible. So ideally, everything runs in the same compartment, the same permissions. And if you make it smaller and everyone has their own system that are not connected, isolated on the network, can't see each other, no connections, then for an attacker, this would be very frustrating, because I can't get a lot of money out of that. Just as maybe as a side quest, because I feel this is connected. Compartmentalization works. That's why we have site isolation. If I undervolt my computer, is this equal to plundervolting myself? No, it's not. Why is it not equivalent? Because you will not undervolt it so far that you get faults. Because if you get faults from time to time, your system would crash. You don't want that. So you would go with the curve a bit higher, so that none of the instructions fault on your specific system. Why does Intel not sell your computer at this level? I was on a plane just on Saturday, because I had to go somewhere for a PhD defense, and I went there in person. Yeah, maybe I will not do that in the future, because it's a lot of traveling for just a PhD defense. Anyways, my undervolted laptop crashed, while on the ground it runs totally stable at this undervolting level. But up in the air, you have more exposure to cosmic radiation. This actually, you also notice that like one long haul flight is the same as getting an X-ray, right? That's what they roughly say. You are exposed to a lot more radiation, and up there, just one of those particles needs to hit my processor at the wrong time, and I get something wrong. But down on Earth, everything's fine. So why does Intel not sell your processor already undervolted to that level? Because they don't know where you are operating this. Whether it's, I don't know, whether it's on an old microwave oven and you have the laptop right on that or next to that, or whether you are using it on the plane all the time. So your computer has to be stable at all usage scenarios. Even if you have, I don't know, some jewelry that is radioactive, it should still work to a reasonable extent. That means you have to make sure that the margin is larger because they didn't introduce security. If they would have security mechanisms, then they could reduce this margin. Is it equivalent? No, because you will test it out and then put it on a value that works for you. Is overclocking a CPU margin? Overclocking a CPU marginally can also bring fault injection. Yes, overclocking and undervolting is the same thing. In the one case, you leave the voltage where it is, but you increase the frequency. So the relation between voltage and frequency is not the same anymore. In the other case, you leave the frequency the same and reduce the voltage. So the relation between voltage and frequency is not the same anymore. So you have the same effect. Yes, overclocking, you could also mount attacks with that. Just the same. It's exactly the same. Now my audio dropped out.
Yeah.
Oh,
No, but I
okay.
guess I would say this is the last question because I have to go into the next lecture.
Okay. So we do have efficiency optimization, but then as humanity just use this to increase shareholder value to do more compute, not to curb emissions in total. Is there any way to avoid this? Also a tough question. Very tough question. I don't have a good answer to that. I think there are a lot of things that we're not doing the right way. I think wasting energy still doesn't, it's not, wasting energy is not, if we know
Not hurting. It's not
if
hurting
we know
enough.
yes, it doesn't hurt to make the computations more efficient. Maybe we are saving a bit, even if overall we are still doing more compute, maybe we are saving a bit. I don't know. I think if everyone contributes a bit, maybe we gain. If you think about it, we need to bring down the emissions very, very far. If a single sector of our global industry, if a single sector does not join us in the fight to reduce emissions, we will fail. So we have to, in computation, we have to figure out how we make it more efficient, how we get to zero emissions. And yeah, if we don't contribute, we will fail.
Don't wait for the others, start yourself, no? I have to say, really, I have to stop it now since the other students in the other course are already waiting. Excuse me. Daniel, as usual, it was amazing. It was a pleasure having you. Thank you to the audience also, and see you next time. And please share the slides if possible, so we can put all the slides online.
Sure.
Thank you very much. Goodbye.